Hey everyone, welcome back to Trigonometry. This will be lecture 8 of the course, and this might be a slightly shorter lecture. I just want to give some attention to applications of trigonometric functions. So let's go ahead and jump into it. We'll call this section 2.4 Applications of Trig Functions. Right? The reality here is that the applications of trig functions are countless. There are so many that you could never enumerate them all. We're going to touch on a couple of them, right? And so obviously the applications we're going to look at here are kind of entry level, but trigonometry applications can get as complex as you could possibly want. So we'll start with some kind of elementary applications here. So the first one I want to talk through is one that's kind of fundamental and something that we'll talk about in more detail later, and that's the solving of a right triangle. Okay, so our first example is going to be solving a right triangle. Okay, and so what do we mean by solving a right triangle? Well, if I've got a right triangle here, let me draw you one. And let's say I've got, I denoted A, B, C for the angles, and this will be the right angle over here. And I denote the opposite sides by lowercase letters. So I've got A, B, C, like that. And let's say I've got an angle over here, maybe 34.5 degrees. That's the one we'll use in the example. What I mean by solving the right triangle is I want to know what all three angles are, and I want to know the lengths of all three sides. Right? So in this example, I don't have enough information to solve the right triangle, but if I put a length on B, maybe I'll say B is 10.5 units, whatever the units happen to be, inches, we could say. But let's say I have this information. I know that this angle here is 34.5 degrees. I know that one's 90 degrees because it's a right triangle. And I know the length of this side. That's enough information for me to determine all of the rest of the angles and all of the rest of the sides for the triangle. And that's what we mean when we say solving a triangle, right? That the word solving means find all the lengths and all the angles. Okay, so let's go through this example, and you'll see obviously where the trig functions come into play. So the first thing I can figure out is I can easily figure out angle B, right? I know angle B is going to be equal to, well, this angle plus this, the sum of the three angles is 180 degrees, right? So what I can do is I know that between these two angles, I must have 90 degrees, right? Because this is a 90 degree angle. 90 plus 90 is 180. So this angle here is basically 90 minus whatever this is. So I can write that 90 degrees minus 34.5 degrees. Right, and that's just a simple bit of arithmetic, and you can do that calculation. You'll see that it's approximately 55.5 degrees. Okay, so now I know this angle. Right, so I've got angle B. It's just a simple subtraction. Okay, so I've got all three angles. Now, I'll just put that information on there just so we know what we've got. Got all three angles. What I want to do next is solve the sides. I only have one of the sides, so I can't use the Pythagorean theorem. If I had two sides, I could. But since I only have one, I'm going to have to use the trigonometry. And so there's a couple of options that you could employ. Let's just use the tangent function to start with. So the tangent of 34.5 degrees, right? What is the tangent equal to? Well, it's equal to the opposite over the adjacent. So let's write that in here. Right, like so. Right, and we know that in this case, opposite is this unknown side, A, and the adjacent side is B, which is 10.5. Okay, and so I can calculate A by just doing a little bit of algebra here. I can see that A is going to be equal to 10.5 times the tangent of 34.5 degrees. Okay, and so I can easily figure this out. I can pull out a calculator, first I calculate the tangent of 34.5 degrees, and then I multiply that result by 10.5. And when I do that, I get 7.22. Okay, so that means A is equal to 7.22. Now, the only thing left to find is C, right? I have options at this point. I could use the Pythagorean identity, a squared plus b squared equals c squared, or I can use the same trick as what I just used with the tangent, and I could use maybe the sine or the cosine, or I could use, well, the sine or the cosine basically. So let's go ahead and use the cosine. And so let's set this up. So I know that the cosine of 34.5 degrees, cosine is equal to adjacent over hypotenuse, isn't it? Okay, that's just the right triangle definition of the trig function cosine. So the adjacent side is b, the one we're given. We know that that's 10.5. And the hypotenuse is c, that's the unknown side that we need to figure out. And so we can multiply here, or do a little arithmetic. Basically, I'll multiply both sides by c and then divide both sides by cosine of 34.5 degrees. But you'll see that I get c is equal to 10.5 divided by the cosine of 34.5 degrees. Looks just like that. And again, you can just use a calculator to figure out what that cosine value is equal to, and then divide 10.5 by that number. And when you do that, you get 12.74. Okay, so this is 12.74, that side C. Okay, and so now you can see we've got B, A, and C, and we know all the angles as well, right? This triangle is solved. Once we know all the angles and all the sides, which we have. Okay, so that's our first application. And so as you can see, anything you can model with a triangle, being able to solve the triangle is going to help with your, deriving a solution for anything that can be modeled using a triangle. Okay, and so our next example is going to be just that. We're going to model something with a triangle. We're going to model a scenario with a right triangle. Okay. So example 2 is going to be a model where we use a right triangle. Okay. So here's the situation. So let's say I've got a tower. Okay, I've got some kind of a tower. This is going to be the most horrible drawing of a tower, but that's okay. Right, so we've got some kind of a tower here, it looks like. Terrible tower. Okay, so the tower is some height which is unknown. We'll denote the height by h. Our task is to figure out how tall this tower is. Okay, and so let's say you're standing off to the side of the tower somewhere, maybe over here. Well, yeah, that's fine. This isn't drawn to scale. Let's say that from the center of the tower to where you're standing is 125 feet, right? This is something you could figure out. You can't climb the tower to figure out how tall it is, but you could just stand at the base and then march off, 125 feet. That's not a problem. And let's say you're looking at the tower, the peak of the tower, there's a line of sight. And they make specifically instruments that can tell you, given the line of sight, what the approximate angle is from where you're standing. And so let's say in this example, when I march 125 feet off the base of the tower, the line of sight angle here is 57.2 degrees. Okay. Question is, how tall is the tower? And so just kind of looking at this, you can pretty clearly see that this could be easily modeled using a triangle, a right triangle. And so just to make sure we're perfectly clear, we've got theta equals 57.2 degrees. We've got 125 over here, and we've got h over here. And this is, of course, a 90-degree angle. And so the question is, can we figure out h if we know these other two items? And yeah, we can pretty easily figure out what h is using one of the techniques from the previous example where we were solving the right triangle. In particular, we can say that the tangent of 57.2 degrees, which we know is equal to opposite over adjacent, and I'll just write that in here so that everybody can keep up with that. The opposite over the adjacent, in this case, is going to be h over 125. Okay. And so given this information, we can again use a little bit of algebra, and we see that the height of the tower is equal to 125 times the tangent of 57.2 degrees. All right, it's just that simple, right? This is simply a triangle, and this is exactly like solving the triangle for the side h. Right, and so you can plug tangent of 57.2 degrees into a calculator, you'll get some number, and when you multiply that by 125, you should get h is equal to, and this is approximate, so let's make sure we're clear on that. The height is approximately 194 feet. Okay. Right, so according to your calculations, the height of the tower is approximately 194 feet. Okay, perfect. So that's a nice example of just modeling a scenario using a right triangle. Let's take this same idea and do something slightly more complex. Slightly more, not much more, but a little bit more complex. Okay, let's say that, let me find my example. Okay, let's say that you go to a hot air balloon ride with your friend, and let's say that you're on the ground and your friend is taking like a hot air balloon ride, right? And so you've got like a basket here and a hot air balloon. Okay, and so you're standing off to the side here. Let's say you're down here, right? You're down here standing. Let me just draw a little stick figure so you can see this is you. Your friend is in the balloon, right? And you're approximately 100 feet from where the balloon took off. Okay. And you look at you're taking a video of your friend, and you're kind of you notice that at one point in the video, your friend is this high. Okay, and we'll call this A. Okay. And at that point in the video, you note that he's 31.7 degrees off the ground. Well, that's the line of sight angle, just like in the previous example. Right? And then a minute later, you notice that your friend is quite a bit higher up here. Okay, quite a bit higher. And again, you've got a line of sight tool, and so you're able to see that at this point, the angle has grown quite a bit, and specifically it's grown to 76.2 degrees. Okay, and so the question is, how much did the balloon climb between these two calculations? So let me write that down. How much did the balloon's elevation change between the two observations? okay, between the two observations. Well, right, so think about it like this. At the first observation, we were a units, a feet, we'll say, off the ground. At the second observation, we were b feet off the ground. Both of these observations can be modeled with a triangle, right? What we really need to know, the question is, how much did the balloon's elevation change? So what we need to know is, what is b minus a? Okay, we need to know what is b minus a. B is the height at the second observation. A is the height at the first observation. What's the difference? Okay, so let's just model these two. So you got two triangles implicitly here. And I won't draw these to scale. There's the first one, and that's, we'll say B. And you got 76.2 degrees. And the second one, we'll say, is this one, and that's A. And here you've got 31.7 degrees. All right, can we figure out, oh, and then both triangles have 100 as the adjacent side. Can we figure out what B and A are? Sure. Right, we know the adjacent side, we need to know the opposite side, so a good candidate here would again be that tangent function. Right, so let's start with A. We'll say the tangent, I'm going to put them down here actually, the tangent 31.7 degrees is equal to the opposite over the adjacent. Right, so that's A over 100. Okay, and so we know therefore that A is equal to 100 times the tangent of 31.7 degrees. And you can do that calculation and find that the height A here is 61.8 feet. So that's the first piece that we need. And so we know that at the time of the first observation, the balloon, your friend in the balloon, was about 62 feet off the ground. Okay, what about the second observation? Well, it's really the same calculation with just different numbers, isn't it? So the tangent of 76.2 degrees is equal to the, again, opposite over adjacent, which in this case is B over 100. And so B is equal to 100 times the tangent of 31.7 degrees. Okay, and that calculation will result in 407.1 feet. Right, so obviously the balloon has climbed a lot in that interval of time. Okay, and at this point you're basically done. You just need to subtract the two numbers. So we'll say the change in elevation is just B minus A, which is equal to 407.1 feet minus 61.8 feet, which, when you do that math, what do you get? You get 345.3 feet. And so the balloon moved up 345 feet in that interval of time. Okay. All right. Very good. Okay, and so you can imagine this type of application where you're modeling some kind of a scenario with a right triangle. The physical scenarios are endless, right? So you can come up with all kinds of examples like this. Okay. All right. So let's move on. And so the second kind of class of examples that I want to talk through are examples using what's called simple harmonic motion. Okay, and we'll talk this through for a second here. I'll give you some idea of what this is. This is a concept that comes up a lot in like physics, particularly like mechanics. Early physics courses will utilize these types of problems a lot. Right, so the idea here, and I'm just going to give you a physical scenario to kind of grasp onto, but let's say you've got a ball or a weight or something, right, and it's attached to some kind of a spring. right? Now if I pull the ball down and I release it, it's going to shoot up and it'll kind of bounce around, won't it, on this spring. If I instead pull the ball up to the top and then release it, it'll do the same thing. It'll bounce around. It just has a different starting point. Right, so you can imagine this ball kind of going up, going down, following some sort of a pattern. Right, now, if I were to take this ball and attach a very particular kind of spring to it, and I pull it down and displace it from its resting position a certain amount, then I'll get a very specific kind of pattern. And so let's just kind of I'll just draw you a picture. Maybe at time 0, well, let's put an axis on here. Let's say, just do it like this. So we'll say this is d equals -1, and then maybe up here d equals 0, and then maybe, let's see, 2, 3, so 1, 2. Up here we'll put d equals +1. Okay, and d here just means distance, right? So maybe at rest d is equal to 0, right? When the spring finally settles down and the ball lands where it's going to land and it stops bouncing, it'll stop bouncing at 0. But let's say at time 0, I stretch the ball down to d equals -1, right? So at time 0, it's down here. Now, if I release it, let's say at time 1, so at time 0, it's down here. At time 1, it's come up a bit, and it's now at d equals 0, so it's at its resting position. But remember, I released it below, so it's shooting up. So it's not gonna rest here. It's gonna keep going. And maybe at time 3, the ball is all the way up here. It's compressed the spring all the way down, and it is at d equals 1. Well, then what's going to happen? What's going to happen next, right? The ball is all the way at the top, and gravity's going to pull it back down, right? So maybe at time 3, the ball is back down at its resting position, right? And then at time 4, it's going to shoot down even further. And we'll just say, for the simplicity of this model, that it goes all the way back down to this position here. Right now, in reality, the spring will absorb some of that motion, and it won't make it quite down to its starting position, but maybe it'll get close. Right? For the purposes of this model, we'll say it does this. Right? And then what's going to happen next is it's going to come back up. Right? And it'll be there, and then eventually at the top. Now, if you kind of think about this, you can see that what's happening here is the ball is following a very particular kind of path. Right? It's following the path of in this case, a sine or cosine function, isn't it? Right? It's kind of starting low, it comes back up to a peak, and then it goes back down to the bottom again, then it comes back up to the top again, etc. Right? This is an example of what we mean by simple harmonic motion. Okay? All right, so let's sort of define simple harmonic motion. Right, and this is going to be kind of a loose definition. We're just trying to gather some intuition here and see how things like this how trig functions can be used to model things like this. Right, so maybe we say that an object is in simple harmonic motion if its distance from the origin, in this case, we'll call that distance d, at time t is given by either, right, it's given by either d equals a times cosine of omega t, or d equals a times the sine of omega t. Okay. Right, and so this is an example where if you just kind of look at this, you can see that this is an example where the motion of the of the ball going up and down, with stretched out over time. Here as another axis. It looks just like a sine or a cosine function, doesn't it? It closely resembles the graph of either sine or cosine, depending on how you want to shift either of those functions. Okay. Now in this case, we know if we look at these formulas a little closer, the A here, we know from our section on graphing these, we know that that's the amplitude. We know that that's the amplitude of the sine or cosine graph, right? It's the how much the sine or cosine function is stretched above or below 1. Okay, and so that's the amplitude, and we also know the period. Right, the period we know is equal to 2 pi over, in this case, omega. Right, there's no displacement here, right, and that doesn't come in anyway, so there's no phase shift that we have to worry about. We're just going to worry about period and amplitude, right? So this omega, this coefficient on the argument t, when you divide 2 pi by that coefficient omega, then you get the period. Now remember, the period is how long does it take before the object starts to repeat itself. And so in our example, one period is between time equals 0 and time equals 4, right? The ball repeats itself after that interval, right? So you could say that the next interval would start here, and it would go from time 4 up to what, 5, 6, 7, time 8, right? So this is what we mean by simple harmonic motion. And of course, I should say omega is greater than 0 here. Okay. All right. So let's kind of use this idea to model a ball on a spring. Okay, so let's use this example, or use this technique to model a ball on a spring, kind of a simple sort of thing. So let's say we have a ball on a spring. So a ball on a spring, and let's say we pull it down, so it's pulled 4 inches below its resting position. So it's pulled 4 inches below its resting position. Okay, and then it's released. So kind of similar to the drawing we have up here. Here's the resting position, d equals 0, and we pulled the ball down. In this case, we just pulled it down to -1, but let's say we pull it further down to -4. And then we release it. Well, we know it's going to shoot up, and then down, and then up, and then down. And we're going to see a pattern very similar to what we have here, aren't we? Right, but just deeper valleys and higher peaks. Okay, so a ball on a spring is pulled 4 inches below its resting position, and then it's released. Okay, and let's say that the period of the motion, is 6 seconds. That's a very long. That's a very long period, right? But it takes 6 seconds before the ball starts to repeat itself. Okay, so the period of the motion is 6 seconds. Our task is to write an equation for the ball's simple harmonic motion. So write an equation for the ball's simple harmonic motion. All right. Now let's think about what this equation has to accomplish, right? Three things really have to be accomplished by this equation. So first thing is it needs to describe D. So the equation needs to describe D, right? And D is the distance above or below the resting position. Okay, right? So the ball's just really in one spot and it's going up and down, right? But predictably, right? Predictably. We just need to be able to write an equation that predicts where the ball will be after a certain number of seconds, certain amount of time. Okay, so that's the first thing. And so the second thing related to that is that the input to the equation needs to be t, or time, right? So the argument / input, however you want to think about it, needs to be time, which we'll denote by t. Okay, so the argument, the input needs to be time, which we'll denote with t. Okay, and then the third thing, I'll put it right down here at the bottom, it has to have a particular form because this is simple harmonic motion, right? So we're asked specifically to write an equation for the ball's simple harmonic motion. And so the formula needs to resemble, it needs to be a cos omega t or a sine omega t, right? So simple harmonic motion, right? Maybe there's another way to model this, another function that could be used, and it probably is. But this is a simple harmonic motion problem, so we want to use this sine cosine. Okay. Okay. So let's go ahead and do this. Let's talk this through. Let's talk through what this needs to look like. So what's the information that we're given? Well, we know at time 0, what's the position of the ball? At time equals 0, the ball's position is d equals 4, right? It's 4 units away from the resting position. But remember how we phrased it, the ball is on a spring is pulled 4 inches below its resting position. So at time t, d is equal to, we'll say, -4. Okay, so just make sure we're clear on that. Here's d equals 0, right? At time t equals 0, we've pulled it down, right? This is where the ball wants to rest, right? But we've pulled it down to d equals -4. And as soon as we let go, the ball's going to shoot up, right? And it might get up here to maybe d equals +4, right? But it's starting down here. It's starting down here at the bottom. Okay. Right? And so we could use cosine or sine, but what's nice, if you remember what the cosine function looks like, it starts up here at the top, right? And it goes like this, right? This is the cosine, right? And this is +1, and down here is -1, right? This is what the cosine looks like. But it's very simple to flip the cosine function to look like this by writing it as negative cos t. Right? And so if we're going to have a coefficient in front of the cosine function that's negative, then the cosine function is the natural choice to use, because it'll just flip, it'll flip the starting point, right, by just putting that negative up front. So our model, so our model will be based on, and we'll write d equals a cosine of omega t. Okay, and so we already can kind of probably see what a needs to be, right? A is the amplitude, so a is equal to the amplitude. And what is the amplitude in this example? Well, if I stretch the spring all the way down so that the ball is at the -4 position, 4 units below the resting position, then is it going to ever go lower than that? Probably not, right? I mean, it's possible that the spring could be very weak, and maybe it shoots up and then gravity is going to pull it down even further. I suppose that's possible. But in general, we wouldn't think that a spring would behave like that. We would expect that when we pull it down, then when it comes back down to the bottom, it's not going to go any lower. And for our purposes, we'll assume it just goes up and then comes right back down to that same position. Right, so we can kind of think of the amplitude as being 4, right? And since we want it to start at the bottom, we'll say the we'll let A equal -4, right? So in this case, the amplitude is 4, and our model should be D equals -4 cosine of omega t, right? Remember, it doesn't matter if it's +4 or -4, you're going to get the same amplitude because it's defined to be the absolute value, but by setting it equal to negative, that's going to specify that it starts in the down position and then goes up, right? Now, if the reverse were true and we pulled it all the way up to the top here at 4 and then let go, then we'd want to use a +4. But since it's being stretched in the negative position, it's starting down there, we want to use -4. Okay. All right, so what is left to be determined is this omega value. So next, what is omega? Well, omega, remember, is related to the period, right? And we're given some information at the onset in the description of the problem. We're told that the period is 6 seconds. So we are told that the period is equal to 6 seconds. Okay, and so we know that the period is equal to 2 pi divided by this omega coefficient, right? And further, we know that the period is equal to 6 seconds, right? So that being the case, we can figure out what omega is by just doing some algebra, right? So this is going to imply that omega is equal to 2 pi over 6, which is just pi over 3. Okay? And so what that's going to do, it's going to say, hey, let's stretch or shrink this period so that it aligns with whatever we plug in for t, and t in this case is in seconds. So adding omega equal to pi over 3 aligns the period, well, aligns the model period, the model's period, with, in this case, the observed period of 6 seconds. Okay, and so our model then is just simply D equals -4 times the cosine of omega t, which, well, is D equals -4 cosine of pi over 3 times t. Okay. All right, so that's the model. That's the model. And for whatever value of t we plug in, this model is going to tell us approximately where the ball is on this up-down axis above or below d equals 0. Right? So if the model returns d equals 2, it's going to tell us that at whatever time the ball is right in the middle. And if we plug in a different time and we get d equals 2 again, we'll know that it's somewhere in the middle, and then it's going to be down here somewhere, and it's going to be all over the place, right? So let's do an example. Let's plug a value into this. Let's plug a value in. This is kind of I guess, an example of using the model. Let's say, where will the ball be in 2 seconds? Right, so I'm holding the ball down at -4, and then I let go. 2 seconds later, where's the ball? Well, it's a simple matter of plugging it into the equation. So d is equal to -4 times the cosine of pi over 3, in this case, times 2 seconds. Okay, and so I get -4 times the cosine of 2 pi over 3. All right, and I can go look that value up. Cosine of 2 pi over 3 is something that you'll find on your unit circle. And so 2 pi over 3 is up here. And so you get -1/2. And so we can just plug that in here, like so, and you'll see that I get what? Do I get -4 over -2? So I just get 2, right? So what does that mean? Well, it's probably an awful lot like what's going on here. The ball starts down here, maybe at 1 second it's here, and at 2 seconds it's up here at d = 2, right? So this is where the ball is at time equals 2 seconds. Okay. Very good. And I could plug in other values, right? And actually we know, right, because we know that an entire period takes 6 seconds, so the ball has taken 2 seconds to go from the bottom up to this spot here. We know it's going to make it about up to d = +4, right? That's the amplitude. And then it's going to start making its way down. But at t = 2 seconds, it's approximately at d = 2. Okay, perfect. All right. And then a simple extension of this idea is to bring the concept of frequency into the discussion. So we've all heard the term frequency. Right, the term frequency. So what is frequency? Well, frequency describes the number of complete cycles per unit time. Okay, so frequency describes the number of complete cycles, right? Complete cycles per unit of time. Okay, right? It's per unit of time. Now, frequency actually turns out, and we just usually denote it with an F, it's actually the reciprocal of the period. Okay, so it's the reciprocal of the period. So you can think of F as being equal to 1 over the period, which we know the period is 2 pi over omega, right? So it's 2 pi divided by omega, and so the frequency would be omega over 2 pi. Okay, now in this case omega is greater than 0, so keep that in mind. Okay. And so let's identify, given our previous example, let's figure out what the frequency of the ball is, right? So the ball in our previous example starts out low, and then it comes up, and then it goes back down, and then it comes up, and then it goes back down, right? So it's got this kind of oscillating behavior, right? And we know that it repeats itself every 6 seconds. Right, and so the question naturally would be, what is the frequency of the ball in this model? Right, and remember, the frequency is going to describe the number of complete cycles per unit of time. Now remember, the period was given in seconds, and so whatever we calculate as the frequency is going to be in seconds, right? So we'll be identifying the number of complete cycles per second with our model, right? So in our case, remember our model was d = -4 cosine of pi over 3 times t, right? Did I write that correctly? Yes. Okay, so this was our model. Right, so the frequency in this case is just equal to omega over 2 pi. Right, so omega was pi over 3, and we're dividing that by 2 pi. And you can think of 2 pi as being over 1, and so we can simplify this as pi over 3 times 1 over 2 pi. The pi's will cancel, and you get 1 over 6. Right, so the frequency here is 1/6 of a cycle per second. And that makes sense. Right, it takes 6 seconds to do an entire period, so it's 1/6 of a cycle per second. Right, that should be pretty obvious. Okay, perfect. Right, so now we know the frequency of our model as well. Okay, I think we'll end it there. As I said, the applications of trig functions, applications that involve trig functions are basically endless, and so we just wanted to do a specific handful of examples just to kind of get you thinking about it, and there will be more to come as well. In particular, we'll figure out more complex ways of solving solving triangles, and specifically triangles that are not right triangles will come up later in the class. All right, but this kind of ends the first bit of the trig course. I really kind of think of the trig course as having basically 3 sections. The first section is what I would sort of loosely just term trigonometric functions, right? And then the second section is what I would call analytic trigonometry. So we'll be moving more into what I would call analytic trigonometry next. So analytic trig is next. Okay, and so now we know what the trig functions are. Let's go see a bunch of the crazy relationships that exist between these things, and that's coming up next. So we'll go ahead and leave it there, and we'll talk to you all next time. Take care.